Welcome to Investigation 3.3, Examining Patterns of Change. Our focus question for this investigation is describe the pattern of change between the number of people on a team and the number of handshakes that occur. So if you remember, we were working in 3.2 on handshakes between team members. So we had team members on one side of the team and team members on another team. And we were determining how many handshakes would occur between the various people and that sort of thing, and we found some interesting quadratic equations. We also looked at the number of high fives that would occur on one team depending on how many people there were and seeing how many high fives would occur, and we found that there was a slightly different pattern with those high fives than the actual handshakes between teammates. So we were able to create some equations that worked with those scenarios. So your job is to essentially take those graphs, take those equations, and make graphs and tables for each of those three scenarios. So we're going to go through the first one together, and then after that we're going to look at the two others that I've already created and synthesize what's going on. So we have our first case, which if I believe there was 5 people on one team and 5 people on another team, and we needed to see how many handshakes would occur between those 5 people and 5 people, and we found that that was 5 times 5, or 25 total handshakes. Then we also looked at if there were 10 people on each team, it was 10 times 10, or 100 total handshakes. So we could use that information to make an equation, and we got the number of handshakes was equal to n squared. So n being the number of people on each team. So this investigation wants us to make a table. So let's zoom in. Let's make a table. So our table is x versus y, and they want us to make a table for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different people on a team. So if there was up to 10 people on each team, how many handshakes would occur? So if there was one person on each team, each of those individuals would come together and they'd have one handshake because it would be 1 squared or one handshake. If there were 2 people on each team, it'd be 4. 3 people on each team, we'd have 9, 16, 25, 36. We're looking at those squared numbers. My favorite number, 49, 64, 81, and 100. So that's what our table would look like if we used our equation n squared, where we're essentially putting, I guess, n or x into that n and then coming out with an output of h, or the number of handshakes, which we're seeing as y here. So after that, we need to graph this baby. So thinking about this table and our graph, we are going to say, okay, at 1 we have 1 handshake. At 2 we have 4 handshakes. At 3 we have 9. At 4, we're at 16. At 5, we are at 25 handshakes. At 6, we're at 36. At 7, we're at 49. 8, we got 64. At 9, there's 81. And 10, we are at 100. So if we were to graph all of this and sort of connect the dots, I'm connecting the dots in a funny way, mainly so we can see our data points. We would see that we have a parabola that continues up. So we have one part of a parabola. Sorry, my graph's a little shaky. So we need to essentially make a table and graphs for each of these 3 scenarios. So I have also made a graph for the next scenario. So the next case was, what if one team had 5 people but the other team had 4 people? What if one team had 8 people and the other team had 9 people? How many total handshakes would there be? And what we find is one team has a higher number of handshakes and the other team has 1 less. So if you had one team that was 6 handshakes, the other team has 7, and so, or 7 people, and so there would be 1 more handshake per person for that scenario. So I created the equation n is n times n minus 1. Or n squared minus n. And from that, I was able to make this table. Now, depending on how you looked at this problem, if you were thinking that the bigger team is the one that we'd have the handshakes, you would have n be that bigger team, or if you looked at it from the team of the smaller, with the smaller number, you could potentially have the equation of this, n times n plus 1, depending on how you looked at it. I looked at it in this manner, obviously. So I created this equation that we have here. You can see my graph. The very last scenario was that of teammates giving each other high fives. So if you looked just at 3 or 4 people, or at 4 people, you would see here's the team, the people on the team, and if they were to give each other high fives, one person would give 3 high fives. The next person has already high fived one person, so they only need to give 2 more high fives. The very last person that we have, or the next person we have, only needs to give 1 high five, and the last person now has high fived everybody. So if you added up all those numbers, we'd end up with 6 total high fives if you had 4 people. So looking at that scenario, we were able to create this equation, which actually looks very similar to our triangular numbers equation. So essentially saying the total number of people on the team squared minus the number of people on the team divided by 2 will get us the number of high fives we would do. And here is my graph that I've created to see all that information. So looking at this information, we need to ask ourselves or answer a couple of questions. Our first question is this. We need to describe the patterns of change, that should say of, not if, of change that can help you predict the number. Wow, I made all sorts of mistakes. The number for handshakes or high fives with teams with larger numbers. How are the patterns similar or different? So we need to look at our graphs and our tables for these situations and see how we can potentially predict bigger numbers. So if I'm comparing my first 2 graphs, if I look at them, my first 2 graphs actually look fairly similar. They look pretty alike. It looks like they have slightly different y-intercepts, just simply because of our 1 on each one of these. My 1 point versus the 1 0 point, so the y-intercept's a little different, or my x-intercept's a little different. What I would say is I see a shift downwards between the 2 graphs by 1 unit, just simply because of this first point that I see here versus this first point that I see here. I think there was a shift downwards between those 2 graphs. If I look at my next graph, though, I can see that there was a substantial difference. This dividing by 2 really changed things. So it changes a lot of stuff there. It looks like our graph is actually kind of smushed a little bit. Graph looks a little flat. Perhaps it's actually even shifted over to the right a little bit. So it looks like it's flat. It looks like maybe one of these other graphs, but maybe cut off about right here. So it's kind of all shifted to the side. So I'm going to say it's shifted right. And that's what I'm seeing between similarities and differences. And I think it's because of our equations that we've used. So how are the patterns similar or different? What we could also do is we could actually look at the patterns between our numbers. So let's zoom in on our very first graph, or our very last graph. If I look at these patterns that we have going on, I see a +1, a +2, a +3, so I can see a +4, +5, 6, 7, 8, 9 pattern. That's kind of interesting. Let's look at some of these others and see if we have the exact same pattern. Here's my second one. If we look at 0 to 2, we have a +2. The next one is +4. Then we have +6, +8, +10, +12, +14, 16, 18. So that's a slightly different pattern. We're increasing by 2. We're increasing 2 on the number that we're increasing by each time. So if we increased by just 0, or if we increased by 2 previously, the next increase is going to be by 4, and then the next increase will be by 6. So that's kind of interesting yet again. This next pattern that we see, 1 to 4, there's a +3 pattern, +3. Here we have +5, +7, +9, +11, +13, +15, +17, plus, I bet you that one's 19. It is. +19. So this one seems to increase by 2, but it's using odd numbers. It's sort of base to play around with. So yet again, interesting. We all have the same sort of increasing pattern. There's always an increase by a constant number by how they're kind of increasing, but the constant number in this one is 2 that it's increasing by. Same with the next one, but the one previous was only by 1. So maybe that's why it's a flatter graph. As well, there's odd numbers versus evens. Odd numbers are clearly making it so we have a y-intercept of 0, 0, whereas this other one, I bet you our y-intercept is actually at -1. Kind of cool. So those are some patterns that I'm seeing in our situation. Next, we need to be able to compare the graphs. And for this, I actually created the graphs on our graphing equations. And if you look, here is our first graph. We have y is equal to x squared. Our second one is that x squared minus x, or n squared minus n. The second one, and our very last one is that one that's super funky, where you have n squared minus n divided by 2. And so if we looked at this really critically, we can see our very first graph is doing exactly what I thought. It is going through that 0, 0 point, and that's where its vertex is. Our next graph over, its vertex looks to be like it's shifted down a little bit, and our very last graph, our vertex is also shifted down. However, they do all go through this 0, 0 point. It just depends on whether they have to dip down into the negatives before they start their upward trend. If we also look at this, we can see that this third graph is flatter. It clearly increases slower than the other graphs, hence that +1 increase. And these other two graphs, if we look at them, they're almost parallel the whole time. They're like kind of, one is shifted over. So our second one, like we thought, is shifted a bit right. And I imagine that is due to this minusing of the 1 in that particular equation. So playing around with this, we can see how the patterns of change have sort of changed the graphs themselves and see how everything works together. So that's kind of cool. Continue with this investigation. If you're confused by any of this, please, as always, ask questions. If you're confused about how to create one of these equations, I can try to help you as best as possible. No matter what, enjoy your evening, and I will talk to you in class.